Side whiteboards. And I have two questions that I'd like you to do. Here they are. To be honest, I did not do the short method first when I did this one. I was like, I'm going to do dot products for my whole time. No. You know that the directional derivative is the magnitude of the grad, right? Times what? Cosine of theta. And in this case, do they give you the magnitude? Yeah, and what's the angle between? Yeah, so it's going to be 5 times 1 over root 2. So you could write that as 5 over root 2, which is the same thing as 5 root 2 over 2. Now, is there a longer method? Yes, because you also know, and you don't have to do it this way, but you also know that FU is also equal to the dot product of two things. What? Grad F dot what? The unit vector dot the unit vector going in the right direction, right? So you know what what direction you're going in. You're going 45 degrees, you're going northeast, right? You're going northeast. So the coefficients of UI, so the U1 and U2, the coefficients of I and J have to be, they're going to be equal, right? It's like 1 over root 2, they have to be the same. Does that make sense, everybody? 45 degrees. If you're going at 45 degrees, what's the slope? Nate, stop. If you're going at 45 degrees, what's the slope? 1, right. So the coefficients, the x, so the ith component and the jth component need to be the same. They need to be the same. So the magnitude needs to be 5. So what is that u going to be? What's that u going to be? I mean, I was just going to let you do it in your head, but you don't have to. We can do it north, right. What is that in vector format, north? J, right. Also known as 0, comma 1, right? So what do you do with these two vectors right here? You dot them, exactly. 5 root 2, 5 over root 2, dot 0, 1, and what do you end up with? 0 plus 5 over. Is that a lot longer of a way to do this? Absolutely, absolutely. The key thing here, what's the key thing that allowed us to do this really quickly? What's the key fact, or what's the key facet of the reality of this word problem that allowed us to do this one nicely? 3 dimensions, I talked to you about how some things are entirely new in 3 dimensions. We're able to do new things completely, but then some of the time it's just what? It's not new things, it's what? They are new, but they're not totally new. They are just what? The same. They're like the same with an added little bit. Like Pythagorean theorem in 2 dimensions, Pythagorean theorem in 3 dimensions. Are they any different really? No, they're not really that different. Same is true in this section. We take a surface and turn it into a contour diagram. That's taking a 3-dimensional surface and turning it into a 2-dimensional representation, right? There are 3-dimensional contour diagrams. We've looked at those. Those are like spheres that are growing or cylinders that are growing. We've looked at them before. Level curves in space. The basic idea is you can have directional derivatives in 3 dimensions. You can have directional derivatives in 3 dimensions. The only thing that changes is this little bit right here. What do we add on? FC, ABC, U3. What is U1? The I component of the unit vector that's going in the direction you want. What's U2? The J component of the unit vector of the direction you want to go in, and so forth. It's the same thing. Nothing has changed except we're adding something in. That's it. Here's the cool thing about it. You can have a gradient in 3 dimensions. Does this look identical to what you just were working with, except there's this little bit at the end? Absolutely, it's the same thing. Now, in 2 dimensions, you could have a contour being carved out like this. The gradient points in the direction of greatest increase, correct? What's the relationship between, if you have a level curve in space right here, and the gradient is pointed off at it, it is perpendicular to the contour. Do you remember that? How the contour is curving through space, and the gradient is shooting off perpendicular to the tangent line, correct? Well, instead of tangent lines, because now we're in 3 space, like a sphere, we're going to have tangent what? Tangent planes, right? So the gradient is going to have what relation to the tangent plane? It's going to be perpendicular to it. When you are constructing the equation of a plane, what are the 2 things that you need? You need a point in the normal vector, exactly. So the big key thing, the entirety of what I really want you to focus on is the fact that if you're constructing a tangent plane, what can you use? The normal, and what's the normal going to be at that point? What's one way to find it? The gradient. If you find the gradient of a certain point for this specific type of function, f of x, y, z, what can you use that to construct pretty quickly? The tangent plane. Because we remember, what's the equation for a tangent plane? A times x minus x naught plus b times y minus y naught, right? Or a, b, and c, that's the any what? That's any what? Any, no, x naught, y naught, z naught is any point. A, b, c is any normal vector. And in this case, how can we find a normal vector? We could just find the